Okay, so for the differential equation, I have J expressed as Jf of ut plus integral of Jc of ut dt. Now, instead of adding all of these constraints from each step, I need to add the constraint of the differential equation, right? So in the discrete case, my constraints are all of these discrete steps. Here my constraint is this differential equation. So how do I add in the differential equation constraint? So if my constraint is a differential equation, how do I add in the equivalent of a Lagrange multiplier? It's no longer a single equation, right? It's a differential equation.
How is that different than what we have?
So what we have is one equation that has to be satisfied. But the differential equation has to be satisfied for every single time, for continuous range of time. This differential equation is true not just for a specific t, it's for all t, right? This is for all t between 0 and my final time big T.
Can we just, like, if we discretize the time, then we can just set each of the n to like the corresponding discretize. Right,
we can discretize that, but like there is a way we can do it without discretization. That is, I can also set my Lagrange multiplier to be a function of t. All right. So here, my differential equation is a function of t. I have to satisfy the differential equation for all t. I can also make my Lagrange multiplier a function of t and integrate it over the time interval. So my u hat is going to be a function of t. And then my differential equation du dt minus f of us dt. Right? This is the new term we are adding. And this actually is equal to 0 for any function u hat of t. It's not just equal to 0 for a constant u hat. It's actually equal to 0 no matter what u hat of t you choose. U hat of t can be a delta function at a certain time. It can be a constant. It can be a sinusoidal function. Any u hat of t, this whole integral would be exactly 0. All right, so with that knowledge, we can start to say, how can I choose u hat of t so that I can cancel out the terms I don't want when I actually express the small perturbation of j as a result of a small perturbation in S. So delta j, following linearization of this formula, would be dj djf du times a small perturbation of u at time t. So that's a linearization of the final cost. And I also want to add in the delta in the control cost. So that's actually I have a partial jc partial u times delta u t dt. And then the term that I added in, which is equal to 0 for any choice of u hat of t, is going to be u hat of t times d delta u dt minus partial f partial u times delta u minus partial f partial s delta s. So in this equation, if we want to compute the resulting delta j with any perturbation delta s, what do we want to cancel in this derivation? Df du is actually known, right? So because f is a known function that like we have to be able to evaluate when solving the differential equation. So what's the term we want to cancel here? What do we not want to evaluate again and again for different values of delta s? Df ds is actually so if we know the solution u, df ds can also be computed analytically.
You have to read that. Oh.
So this, if we want the gradient again, if we want the gradient of j with respect to s, then we are looking at infinitesimal perturbations in s, right? So we can imagine we already solved the nonlinear equation for the u, so we have a trajectory of u stored in the computer. If I want to ask you what is df ds at any time, I can just grab my solution at that time and substitute into the formula for df ds, and I can compute df ds. I can also compute df du, right? But what do I not have? The assumption is I have the trajectory, I have u of t. Now I'm looking at small perturbations around that nonlinear, around that trajectory. I need to consider a lot of different perturbations around that trajectory.
Yeah, so we know u is a function of t.
Yes.
Delta u is u hat is the test function.
Yeah, u hat is so this is true no matter what u hat is. So you can choose the value of u hat in an attempt to cancel something you don't want to evaluate again and again. Right, so imagine like if I give you a delta s and ask you to compute delta j, what would you do? How would you program your computer df ds? So what do you need to compute df ds? Right. Let's just take a more specific example. What if let's just imagine my du dt equal to minus s times u. Right. Here is a parameterized differential equation. So f of u in this case equal to minus s times u. Right. So here, if I want to compute df ds, I should just get a minus u, right? So in order to evaluate this term, I need the solution u, right? So okay, so for that I need to solve for the whole trajectory of u. That's one thing I have to do. But then the question is really, if I choose a different delta s, what do I have to evaluate again and again? What do I just have to evaluate only once? Do I have to compute u again? No, because it's the same u, right? I'm considering it just a different perturbation. Do I have to compute df du again? Df du in this case is just the minus s, right? So if I know what is the baseline s, on which I'm making infinitesimal perturbation, I don't have to compute df du again. How about this?
Yes, because different delta s will cause different delta u.
Yeah, different delta s is going to cause different delta u. So any term that involves delta u it's something I would have to compute again and again, unless I eliminate them from this formula by appropriate choice of U hat. Right, so that's actually what we have been doing in this derivation of the backpropagation. We are doing the same thing, right? So the reason we are canceling all of these delta u's is because these are the terms we have to compute again for different delta s's. So here it's the same thing. All right. So how do we do that? The goal is the same, but the procedure of eliminating all these delta u's is actually a little bit more non-obvious in this case.
Similar to integration by parts.
Yes, we have to integrate by parts. This is because I have a delta u sitting inside the time derivative, right? In order for me to cancel the coefficients on top of delta u, I first have to pull this delta u out of the time derivative. So let's just consider this very term.